Students, here's a classic weak acid problem where they're giving us a Ka value, an initial concentration, and they're asking us to find a whole bunch of other things. Let's start by writing the acid dissociation equation. As you can imagine, the weak acid is going to be the dominant source of hydrogen ions, and so we will make an ice table with that equation. They give us an initial concentration of 0.22 molar, and since they don't mention either of the other species in the equation, you can safely presume that those concentrations are zero. Without even having to calculate Q, we know that we're going to shift to the side with the zeros. So pluses on the right side of the equation and minuses on the left. We'll define those changes in terms of x. The coefficient for all species in this equation is 1, and so it's minus 1x plus 1x and plus 1x, which brings us to the equilibrium line of the ice table, where we get to write equilibrium expressions in terms of x. Now they gave us a Ka value, and Ka is calculated using product concentrations over reactant concentrations. Since everything is aqueous in this equation, everything belongs in the equilibrium expression. And we can substitute the equilibrium line of the ice table for those concentrations. X times x over the quantity 0.22 minus x. Let's go ahead and make the mathematical assumption that 0.22 minus x is roughly equal to just 0.22. In other words, the value of x is negligible compared to the initial acid concentration. And that whole expression is equal to the Ka value they gave us at the beginning of the problem, which was 1.3 times 10 to the negative fifth. Now that we've made that mathematical assumption, the equation becomes a lot easier to solve. I'll simply take the Ka value times 0.22 and then take the square root of that. X works out to be 0.00169. Incidentally, if you didn't make the mathematical assumption and type the whole quadratic equation into your solver feature and found x, the value of x would be 0.00168. Yes, it's a more exact answer, but it took longer, or it would normally take longer, to use the solver feature and carefully type in all of the parentheses. The mathematical assumption, as you can see, gives us a value of x that is very, very close to the more exact value of x, and it got us that value in less time. Now that we have the value of x, we already can find the equilibrium concentrations of both hydrogen and the conjugate base of the acid called propanoate. We can also plug the value of x into the expression for the acid concentration, 0.22 minus 0.00169, and we get 0.218. That gave us several of the answers the problem wanted already. Let's go ahead and record that. The concentration of hydrogen at equilibrium is 0.00169. The concentration of the conjugate base, propanoate, 0.00169. The concentration of the acid, 0.218. To get percent dissociation, we'll use the equation It's going to be the hydrogen ion concentration at equilibrium all over the initial acid concentration, and convert to a percentage by multiplying by 100. So the value of x, 0.00169, the initial concentration of the acid, 0.22, and it works out to be 0.77% dissociation. Okay, what else do we have to find? The pH and the hydroxide concentration. Well, we know the concentration of hydrogen, and we can calculate pH by simply taking negative log of that number. So negative log of 0.00169 gives us 2.77. That's our pH. The hydroxide concentration we can find from the pOH, and we can get that by subtracting 2.77 from 14, and we get 11.23. The hydroxide concentration can then be found by taking 10 raised to the negative pOH power. In this case, that's 10 raised to the negative 11.23 power, and that works out to be 5.95 times 10 to the negative 12th. You should get a pretty small number there.